Hello students, welcome back to the session. So in this session we'll be dealing about the topic review of Bohr's atomic model. So what was the intention of Bohr's atomic model, and there were many atomic models that were proposed before Bohr's in order to explain the structure of atom. So what was the necessity for us to study the structure of atom is, in our previous video we have learned about what do you mean by line emission spectrum, and we have also seen that different atoms will get you different line emission spectrum. That is, line emission spectrum will be the characteristics of the atoms. So our intention is to explain what is the necessity for the, or what is the reason for the line emission spectrum. So there were many scientists who made lot of effort in order to find out what is the reason for the emission of, that is the line emission spectrum, in order to explain the line emission spectrum. So in order to find out the reason for the emission of line emission spectrum, first we need to know about what is atom and what is present inside it. So therefore, in order to explain the atomic spectra, so first we need to know about the structure of atom, so or what is present inside the atom. Okay, so many theories were proposed in order to explain this. So under that, the first atomic model was given by J Thomsom after the discovery of electrons through electric discharge in the vacuum, that is the vacuum chamber. Okay, so according to this atomic model, so according to this J Thomson atomic model, so the atom is consisting of a cloud of positive charges which are distributed throughout the atom. That is, the positive charge of the atom is uniformly distributed throughout the atom, and the negative charges, that is electrons, are embedded here and there like the seeds in the watermelon. So here we can see a comparison between the atom model that was proposed by the J Thomson and with the comparison with the watermelon. So as we can see that there is a red color stuff inside the watermelon, so that red color stuff will represent you the cloud of positive charges. There is the distribution of the positive charges uniformly throughout the atom, and the electrons are like seeds. We can see that black seeds in the watermelon, right? So that will be the electrons that are present inside the atom. So why this type of model was proposed? Because we already know that the magnitude of the positive charges that are present in the atom and the magnitude of the negative charge that is present, so they must be equal in magnitude. So that means the atom is electrically neutral. So therefore he combinedly thought that the there is the atomic model, there is the atom might be made up of like these things. There is cloud of positive charges and the negative charges are embedded here and there, and the amount or magnitude of the positive charge and the magnitude of the negative charge is equal. So this was able to explain the neutrality of the atom. But what is the main failure of this J Thomson atomic model is, see, this atomic model could not give any idea about the spectral series. Of course, it was able to explain the neutrality of the atom, that is, it could prove that is the atom is electrically neutral, but this particular theory or atomic model was failure to explain the line spectrum that is given by the atoms. So why the atoms will emit line emission spectrum? And another major failure of this particular atomic model, that is J Thomson atomic model, was it could not explain the large angle alpha scattering, so which was conducted by Rutherford. Okay, so this is the main failure of J Thomson atomic model. So in order to again explain the structure of atom, another atomic model was proposed. So that atomic model is what we call it as Rutherford atomic model. So actually Rutherford conducted an experiment. Okay, so what he did is he took a gold foil and he tried to incident, or he tried to bombard the alpha particles on this gold foil. So he observed that there is some deviation by the alpha rays. So he was, he was trying to explain why is there is some alpha particles are scattered very large at large angles, and few are undeviated. That is, they are not undergoing any deviation. So in order to explain this, he tried to explain the structure of atom. So that is, according to this Rutherford atomic model, an atom will consist, that is from his experiment, that is large angle scattering of alpha particles by thin gold foil. From this experiment, he concluded that an atom consists of a tiny positively charged core, that is what we call it as a nucleus, which consists of 99% of the mass of the atom, and the electrons will be revolving around this nucleus in circular orbits. This was the structure of atom according to Rutherford. Rutherford actually tried to explain the large angle scattering of alpha particles by the thin gold foil. Parallelly, he was able to explain the Rutherford atomic model. So there is 99% of the mass of the atom is concentrated at the center of the nucleus. So that is what we call it as the core of the atom, that is called as nucleus, and the electrons are revolving around the nucleus. And here also the positive charge that is present on the nucleus will be equal to the magnitude of the charge that is been revolving by the electrons in different circular orbits. Okay, so this was able to explain the neutrality of the atom, and he was able to explain, or he was able to give little bit idea about the atom or atomic model. But there are some limitations for this Rutherford atomic model. So let us see one by one. And one more thing to be remembered is, so that is, from where are we getting this force, for centripetal force for the electron to revolve around the nucleus is, see, any object according to classical mechanics, any object which is revolving in a circular path, so it should be acted by a centripetal force. So this centripetal force will be in the form of electrostatic force of attraction between the positively charged nucleus and the negatively charged electrons. So from this Coulomb force, the electron is able to revolve around the nucleus. That is, the Coulomb force will be acting in the form of the centripetal force. So now let us see the limitations of Rutherford atomic model. So first is, even though it was able to explain the neutrality of the atom, and also it was able to explain that the centripetal force for the electron to revolve around the nucleus is provided in the form of Coulomb's law of attraction, but still there lie some limitations for this. So we have seen this in your paper 5, failures of classical mechanics in order to explain the Rutherford, that is the stability of the atom, right? So under that we have encountered this, but still we have to recall once again all those things. See, according to electrodynamics, any object which is revolving in circular path, it will be acted upon by some force, that is what we call as the centripetal force. And any particle which is moving in a circular path, it will be accelerated. And according to electrodynamics, any accelerated charge must give out energy. So therefore, electron which is revolving around the nucleus is said to be accelerated. So therefore, it is continuously in motion. So therefore, continuously it should give out energy. So therefore, instead of practically what we are seeing line emission spectrum. But according to electrodynamics, we should get the continuous emission spectrum. Hope you remember what you mean by continuous emission spectrum, and you remember what you mean by line emission spectrum. So there is a discrepancy, or there is a mismatch between the theoretical concept and the experimental result that we are getting. So experimentally what we are getting line emission spectrum, but theoretically we are predicting to get continuous emission spectrum. So due to this mismatch between these two spectrums that we are getting, so that is one of the limitation for Rutherford atomic model. So that is, we can see one more thing is, it could not explain the stability of atom. So why is that unable to explain by Rutherford? See, according to electrodynamics, any continuously accelerated charge will give out energy continuously. So therefore, electron will lose its energy step by step, and it will follow the spiral path, and finally it will fall or it will collide with the nucleus. So whenever this electron collides with the nucleus, so the atom will be unstable, that is, it should have been demolished. Okay, so therefore this particular Rutherford atom could not give any reason for the stability of the atom. So therefore, once again, this Rutherford atomic model was a little bit failure to explain the structure of atom. As I said, so that is, we should get continuous emission spectrum according to the Rutherford atomic model, but here what we are getting is experimentally we are getting, there is, whenever you excite, there is gas or vapor which is in the atomic state. So when you excite this, we are getting a line emission spectrum. So this discrepancy could not explain the structure of that is the Rutherford atomic model, was once again a failure. So hence we have to look into another theory which could explain, that is, main intention of proposing atomic model is to explain the emission spectrum or the line emission spectrum of hydrogen atom, that is the simplest atom. Okay, so that was the main intention of everyone. So due to this, they proposed, that is, atom may be like this, it may be like this, but we should be aware that the experimental result and the theoretical result, so both should match with each other. So then only we can accept that particular concept or that particular theory, right? So now let us move on to the next atomic model that was proposed by Niels Bohr. So that is what we popularly call it as Bohr's atomic model. So in order to explain the failures of J Thomson atomic model and Rutherford atomic model, so Bohr made some modifications in the Rutherford atomic model with his famous 4 postulates. Okay, so that is what we call it as the Bohrs postulates. So under that, the first postulate goes like this: there is, any atom will be consisting of a positively charged nucleus according to Rutherford itself, and the negatively charged, definitely it will be revolving around the nucleus in different circular orbits. But the necessary centripetal force, again, it is provided in the form of electrostatics or Coulomb force of attraction between the nucleus and the electron. So on the left hand side of the equation we have mv square by r, that is nothing but centripetal force. On the right hand side we have the Coulomb force, that is 1 over 4 pi epsilon naught q1 q2 divided by distance square. Okay, if you consider that the electron is revolving in a circular orbit of certain radius r, okay, so the distance and charge q1 is nothing but the charge present on the nucleus, and q2 is nothing but the charge of the electron. Charge of the electron is E, right? And the charge which is present on the nucleus is known as Z into E. So what is Z here? So Z is nothing but the atomic number. Atomic number means the number of protons present inside the nucleus. But because why? Because neutron, that is after the discovery of neutrons by Chadwick. Okay, so they concluded that there are protons and neutrons together present inside the nucleus, and neutrons are neutrally charged, protons are positively charged. So the number of protons is taken as the atomic number, right? So that is Z. So if E is the charge of each proton, then Z into E will, this product will get you the number of, that is the magnitude of the charge present on the nucleus, and the charge present on the electron is taken as E. Okay, so this is the first postulate. And the second postulate is, the electron cannot revolve in any orbits, that is, it cannot revolve in any orbits of its choice, right? So it can revolve only in those orbits for which the orbital angular momentum, it should be equal to integral multiple of h divided by 2 pi, right? So m into v is nothing but momentum. When you multiply this momentum with the radius, that becomes the angular momentum. Hope you all know this in your rotational motion. So since it is subjected to orbit, hence we call it as an orbital angular momentum. Okay, so mvr is your orbital angular momentum. So that must be equal to n into h divided by 2 pi, where n is nothing but a natural number, of course, or we will call this n as the principal quantum number. So that will be dealt later on in the next concepts, right? So see, for example, if the electron is in the first orbit, then the radius of that orbit and the velocity of the electron in that particular orbit, of course mass of the electron is constant for particular orbit, let us consider. Okay, so velocity and radius for an electron in some first orbit. Okay, so then you will take n is equal to 1. So this left hand side orbital angular momentum must be equal to integral multiples of h divided by 2 pi. If the electron is revolving in the second orbit, for example, so then the velocity in the second orbit and the radius of the second orbit, when you multiply with the mass of the electron, so this must be equal to 2 times h divided by 2 pi. That is the meaning of this particular equation. Got it? So this is the second postulate, that is electrons cannot revolve in any orbit of its own choice. So it should satisfy a condition, that is it must be equal to integral multiples of, that is the orbital angular momentum must be equal to integral multiples of h divided by 2 pi. So this is the condition. So if the electron is satisfying this equation, then that particular electron can revolve in those orbits. Okay, so this is the meaning of the second postulate of the Bohrs. And next postulate is, that is the electron which are revolving in these orbits. So remember that these orbits, what is these orbits? That is, come back to your second postulate. See, if your condition for the orbital angular momentum, if it is equal to the integral multiples of h divided by 2 pi, so then only that particular electron will be revolving in that particular orbit. So the electron which is revolving in that particular orbit do not radiate any energy, right? Hence these orbits are called as stationary orbits, or it is also called as non-radiating orbits. See, this is a main difference, or which took a deviation in the atomic model, which brings some success to the atomic model that was proposed by Bohr. Why? Because he could not, that is Rutherford could not explain, that is electrons are revolving in the orbits, it should get continuous emission spectrum according to the theory, but practically what we are getting, line emission spectrum. So that was the main discrepancy between the Rutherford atomic model and the experimental result. So Bohrs changed this concept, that is the electrons which are satisfying the second postulate, so which are revolving in these particular orbits, so they do not radiate any energy. So these orbits are called as non-radiating orbits. So, or it is also called as a stationary orbit. So why do we call this as a stationary orbits? Because even though the electron is continuously revolving around the nucleus, it is not giving out any energy. So it seems to be, or it is seen that it remains stationary, or if it will be assumed as if, or the electron will be behaving as if it is at rest. Hence it is called as stationary, or it is also called as, since it is not radiating any energy, so therefore we call it as non-radiating orbits. So this is the Bohr's third postulate. So next and the last postulate, then when we will get the spectrum? So whenever the electron makes a transition from higher energy orbit to lower energy orbit, so the difference between the energy of the higher energy orbit and the lower energy orbit, so the difference in these energy, so whenever the electron makes a transition from higher energy to lower energy state, so the difference in the energy of these two orbits will be given out as the energy of the emitted radiation. So there is the fourth postulate, that is electrons which are radiating energy, that is electrons radiates energy when they jump from higher energy orbit to lower energy orbit. So hence the energy of the emitted radiation will be always equal to the difference in the energy levels, that is h into nu, that is nothing but the energy of the emitted radiation will be equal to E2 minus E1. So E2 is nothing but the energy of the higher energy state. It may be third energy state, fourth energy state, or any one. Okay, just generally we are indicating it as E2. So E2 is the higher energy state, or it is also called as any higher energy state, and E1 is the energy of the electron in any lower energy state. It may be second, or if the electron makes a transition from fifth orbit to what we say second orbit, so then fifth orbit is known as the higher energy orbit, and second orbit will be known as the lower energy orbit. So these are the four postulates of Bohr's, right? So based on this he derived some equations. So now let us see what was the equations that was derived by Bohr and how he was able to explain the emission of the spectral length, that is the line emission spectrum. So how he was able to explain. So with the help of these postulates. So Bohr was able to obtain the expression for the radius of the atom, that is nothing but size of the atom, and wavelength of the spectral line emitted. So the first expression that was obtained by the Bohrs was about the radius of the stationary orbits, and the expression for the radius of the nth orbit is given by r is equal to n square h square epsilon naught divided by pi mz e square, where n is nothing but principal quantum number or is nothing but a natural number, and h is nothing but known as the Planck's constant, epsilon naught absolute permittivity of free space, m is the mass of the electron, z is the atomic number, and E is nothing but the charge of electron. So if you substitute, that is Z is equal to 1, then that will be for hydrogen atom. Okay, so why? Because that is the simplest atom. Atoms were made by all the scientists in order to explain the structure of the hydrogen atom basically first. Then we shall they can try for hydrogen any complex atoms. Okay, so therefore this is nothing but the expression for the size of the orbit, or it is nothing but the radius of the stationary orbit. So, and the expression for the velocity of the electron in the any nth orbit is given by v is equal to z square divided by 2 nh epsilon naught, where all the terms carry their usual meaning. That means z is nothing but atomic number, and E is nothing but the charge of electron, n is nothing but the principal quantum number or natural number, so on. Okay, and with the help of these two, radius and expression for velocity, he tried to obtain the expression for the total energy of the electron in the nth orbit, and it is obtained as En is equal to minus z square e to the power of 4 into m divided by 8 n square h square epsilon naught. So remember, there is some physical significance in this expression, that is En is equal to minus. We can see that there is a negative sign. So the negative sign indicates that the electron is bound to the nucleus and energy must be supplied for the electron to take out from the atom. So there is the significance of the negative sign. So this will be appearing for your concept questions or for 2 marks questions, right? So what is the significance of the negative sign in the expression for the total energy of the electron in the nth orbit is that the negative sign indicates that the electron is bound to the nucleus. That means the nucleus is attracted, or the electron is in the control of the nucleus, we can say, for easy understanding, and energy must be supplied for the electron to take out that electron from any nth orbit. And here, if you need it for hydrogen atom, directly substitute Z is equal to 1, you'll get the expression for the total energy of the electron present in the any particular hydrogen atom, right? So, or this equation can also be simplified, that is, after substituting the value of Z, E, M, 8 h square and epsilon naught square. So, and after converting from joule to electron volt, so finally the expression will be En is equal to minus 13.6 divided by n square electron volt. So this is the expression for total energy. And with the help of all these 3 equations, that is 3 derivations that he has done, I have not shown the derivation, just since we are reviewing that, so therefore only the expressions are important and no derivations are present. Okay, so expression for wave number and wavelength E is given by the equation. See, wave number, what do you mean by wave number? Means the number of waves per unit length is nothing but known as wave number, that is indicated as nu bar. Okay, so you know the symbol for frequency, nu. Upon that, if you draw a small line, that is called as nu bar, and it is nothing but measured as the reciprocal of the wavelength. So therefore nu bar is equal to 1 by lambda, that is equal to r into 1 by n1 square minus 1 by n2 square. So if any electron makes a transition from higher energy state, let it be into, to lower energy state n1, so then this equation, that is 1 by lambda is equal to r into that particular equation, will get you the wavelength of the emitted spectral line. So, and r is nothing but known as the Rydberg constant. So from this equation, Bohrs obtained practically, there is the value of the Rydberg constant that is obtained experimentally and with this particular equation was matching with each other. So therefore we say that Bohr's atomic model was the first successful atomic model in order to explain the atomic spectra or the line emission spectra. So with this help of his postulates, he was able to predict what is the reason for the line emission spectrum. That is, the atoms which are present in the gas or in the vapors. So when they are excited by some means to higher energy state, and the lifetime of the atoms in the higher energy state is very less, when they come back to the lower energy state, so it gives out energy. So the difference in the energy of the energy levels will be given out as the energy of the emitted radiation, and the wavelength of that particular emitted radiation can be theoretically calculated as 1 by lambda is equal to r, where r is nothing but the Rydberg constant into 1 by n1 square minus 1 divided by n2 square. So from this equation, the value of wavelength or the value of the Rydberg constant that is obtained both experimentally and theoretically matches with each other. So therefore the Bohr's atomic model was the first successful atomic model in order to explain the structure of atom. Right now, there was some limitation, but even though Bohr was able to explain his atomic structure, so there are some limitations in the Bohr's theory also. So let us look into what are the failures of the Bohr's theory or Bohr's atomic model. Bohr's atomic model could not explain the intensity of the spectral lines. See, when you observe the line emission spectrum of different atoms, it may be hydrogen or helium or hydrogen like atoms, whatever it may be. So there are some spectra where you can see that whenever few spectral lines are very brighter and few spectral lines are very fainter, that is intensity is very less. So even though he was able to explain the line emission spectrum, but he could not explain the intensity. There are some fainter lines, there is a fainter emission spectrum, few lines are very bright. So what is the reason for this? He was not able to explain. So that is the failure of Bohr's atomic model, and this is again an important concept for 2 marks questions or 3 marks question. That is, mention the limitations of Bohr's atomic model. The first limitation is it could not explain the intensity of spectral lines. Second one is fine structure of spectral lines. So this is very important concept. So what do you mean by fine structure? See, if you see some spectral lines from, for example, if you observe the sodium vapor lamp, we can see doublet, right? So doublet means there will be 2 spectral lines. Okay. So for single transition from higher energy state to lower energy state, so there is from some single transition itself. But if you observe this spectral line with the help of highly resolved spectrometer, we can see that within a single transitions there are very closely spaced lines. Okay, so there is in one transition itself there are many sub transitions that we can call it as. There is in one single transition. So if you observe that spectral line, there are closely packed spectral lines more than one. So this is what we call it as the fine structure splitting. Okay. So what is the reason for fine structure? We'll be studying in our next sessions. Okay. So it could not explain. There is this fine structure splitting of spectral lines was not able to explain by Bohr's atomic model. And next failure is it could not explain the splitting up of the spectral lines in the presence of the magnetic field. That is what we call it as the Zeeman effect. And it could not explain the splitting up of the spectral lines in the presence of the electric field. That is what we call it as the Stark effect. And you are going to study Zeeman effect in the next sessions. That is, we have 2 types of Zeeman effect. One is normal Zeeman effect and another is anomalous Zeeman effect, right? So this particular things has to be kept in mind. So if you place the source which is emitting spectrum in the presence of electric field or in the presence of the magnetic field, and if you observe that particular line spectra, so we can see that a single spectral line will be divided into 2 or more components. So that is what we call it as the splitting up of the spectral line in the presence of magnetic field or electric field. If there is a splitting in the magnetic field, that is called as Zeeman effect, and if there is a splitting in the electric field. That is what we called as the Stark effect. Next failure is it could not explain the spectrum of complex atoms, that is which is having more than one electron. See, if you take the helium atom, we have two electrons which is revolving around the nucleus. So if I take out one electron from this particular helium atom, then it is consisting of only one electron in its outermost orbit. If you take the hydrogen, it is also consisting of only one electron. So now if you take out one electron out of two in the helium atom, then that particular helium atom will be called as singly ionized helium atom. So any atom, if it is consisting of only one electron which is revolving around the nucleus, then we call it as hydrogen like atom. But if you go on if you see the increasing order of the atomic number, we can see that there are more than one electron which is revolving around the nucleus. For example, if you take sodium, that is equal to 11, okay, or if you take carbon, oxygen, there are more electrons, okay, which is revolving around the nucleus. When you excite these particular atoms, so the spectrum that is given by these atoms was not able to explain by Bohr's theory. That is again one of the failure of the Bohr's atomic theory, that is it could not explain the spectrum of complex atoms. That is any atom which is consisting of more than one electron revolving around the nucleus, so those will be called as the complex atoms. And next and the last failure of Bohr's atomic model was it could not explain the filling up of the electrons in various shells and subshells. If you take atomic numbers that is equal to 11, it was not able to explain whether all the electrons are present in first orbit itself or the electrons are distributed in different energy levels or different orbits. So that was not able to explain by Bohr's atomic theory. But still Bohr's theory was the first successful theory in order to explain the structure of atom. Why? Because he was the initial person who was able to explain the spectrum which is given by the simplest atom, that is nothing but hydrogen, right? So hence Bohr's theory is a remarkable theory. Now let us see some that is spectral series of hydrogen atom. So mainly there are 5 series. One is Lyman series, Bohrs series, Paschen series, Bracken series and Pfund series. So when do we get Lyman series? Means whenever there is a transition from higher energy orbit to first orbit, that is N2 maybe 2, 3, 4, 5, 6, 7, 8, anything. But the transition from higher energy orbit, it must directly go to the first orbit, then that particular series is what we call as the Lyman series, and the expression for the wavelength is given by 1 by lambda is equal to r into 1 by 1 square. Hope you remember this equation. There is 1 by nu bar is equal to 1 by lambda, that is equal to r into 1 by n1 square minus 1 divided by n2 square. But here we are going to fix the value of n1 as for 1. Lyman series means n1 will be 1. So you will be having problems based on this. So therefore be careful. So I mean, if it is making a transition from 4th orbit to 1st orbit, then take the value of n as 4. Okay, so the n here we shall take n, that is n2 is equal to n as the higher energy orbit number. And the spectral series that you get, it will be having a wavelength equal to wavelength of ultraviolet region that comes before the visible region, ultraviolet region. Now next series is Bohrs series. This series will lie in the visible region, hence they will be designated as H alpha, H beta, H gamma and H delta lines. Why? Because we can see with the help of the spectrometer, we can see by our naked eye with the help of spectrometer. So therefore they are designated. Why? Because this wavelength range is acceptable by the human eye. So therefore they are designated as H alpha, H beta, H gamma and H delta. Okay. Now when do we get Bohmer series basically? So whenever an electron makes a transition from higher energy orbit to second orbit, not for first orbit, any higher energy orbit, 3, 4, 5, 6, 7, 8, N2 may be 3, 4, 5, 6, 7, 8, but N1 must be equal to second orbit itself. It should make a transition from higher energy orbit to second orbit itself. Then we get the Bohmer series. Since it is lying in the visible region, it will be designated as H alpha, that is the first member in the series, H beta second member, H gamma third member in the series, and H delta is the last member in the series. Okay, and the expression for the wavelength, as usual, we know that in the place of N1 we have just 2, and in the place of N2 we have N. Okay, so therefore it may be 3, 4, 5, 6, 7, 8, anything, right? So this is the second member of hydrogen that is spectral series of hydrogen atom. Next is a Paschen series, that is, this series is obtained due to the transition of the electron from higher energy orbit to third orbit. So therefore N1 is fixed as 3 for Paschen series, and remaining N2 values will start from 4, 5, 6, 7 and so on, and this lies in the starting region of IR, that is in the nearer end of IR. So therefore that is a wavelength range of Paschen series, and the expression for the wavelength is given as the equation. Next is the bracket series, and this series is obtained whenever an electron makes a transition from higher energy orbit to fourth orbit, and this lies in the middle of the IR region, and here N1 will be equal to 4, which is fixed, and N2 may vary from 5, 6, 7, 8, 9 until infinity. Okay, now next and the last series in the spectral series of hydrogen atom is Pfund series, and this series is obtained due to the transition of the electron from higher energy orbit to fifth orbit, and this Pfund series is obtained in the farther end of IR region, and here N1 is fixed and that is equal to 5, and N2 will vary from 6, 7, 8, 9 and so on until infinity, and the expression for the wavelength is given by 1 by lambda is equal to R into 1 by 5 square minus 1 divided by N square. So this is your Pfund series, and this ends about the spectral series of hydrogen atom. Now let us look into the energy level diagram. So what do you mean by energy level diagram? It is nothing but, see, we know the equation, that is En is equal to minus 13.6 divided by N square electron volt. Okay, so here on the right hand side we can see that there is orbit number n is equal to 1, 2, 3, 4, 5, 6, 7 and so on until infinity, and on the left hand side if you substitute the value of n is equal to 1, you will get the expression, value of the energy of the electron in the first orbit, second orbit, third orbit, fourth orbit and so on. Okay, so that is, we have the equation En is equal to minus 13.6 divided by N square electron volt. So hope you remember this equation. It's here. This equation En is equal to minus 13.6 divided by N square. N is equal to 1 means first orbit. Okay, so then you'll get minus 13.6 electron volt. If you substitute N is equal to 2, you'll get minus 13.6 divided by 2 square. That is nothing but 2 square is 4. If you divide 13.6 divided by 4, it will be equal to around 3.4 something. Okay, now so that is mentioned on your left side, minus 13.6 electron volt, minus 3.4 electron volt, minus 1.51 electron volt, minus 0.85 electron volt and so on. If you go, I have taken only 4 values. Okay, so here we can see how is the spectral series obtained. See, if we can see that whenever there is a transition from second orbit to first orbit, third orbit to first orbit, fourth orbit to first orbit, you are getting Lyman series. Similarly, Bohmer, Paschen, bracket and Pfund series you can see, right? So these are the this is what we call it as energy level diagram, and observe that the space between the first orbit and the second orbit is little bit more, second and third is less, third and fourth is little bit less, again fourth and fifth is again less, and it is merging out. It means that as we move away from the nucleus, we have to remember two things. The energy gap between the energy levels goes on decreases, and the energy of the electron increases. Why? See, you have to observe that negative sign. We have a negative sign there. It is first orbit is minus 13.6. minus 3.4 is greater than minus 13.6, right? You know that. So second, I mean, when you compare the electron which is present in the first orbit and the electron which is present in the second orbit, so the electron which is present in the second orbit is having a greater energy when you compare with the electron which is present in the first orbit. Why? Because it is minus 13.6 and this is minus 3.4. So therefore we have seen that the valence electron are having higher energy, and usually valence electrons are taken out. Why? Because if you supply very little bit energy, right? Okay, so if you divide minus 13.6 divided by 10 square, it is minus 0.013 something, right? So small amount of energy if you provide, okay, so then easily the electron can come out from that particular energy level. So therefore as the value of n increases, right, as the value of, that is, if you increase the orbit number, the energy of the electron goes on increases. So therefore the outermost electrons will be having larger energy when you compare with the electron which is present in the innermost orbits or the first orbit. So this is what we call, that is that can be understood with the help of this energy level diagram. So next we have to look into two important concepts, that is ionization and excitation. So first let us look into the concept of ionization. So the concept of ionization says that, so it is nothing but the process of removing an electron completely from the atom or taking the electron which is present in any orbit, so to the orbit which is at infinity. So that means completely we are taking out of the electron from the atom. So this process is what we call it as ionization, and the energy required to remove the electron from the ground state to infinity or completely from the atom is called as ionization energy. If ionization energy is expressed in electron volt, then it is called as ionization potential. For example, if we have an electron in the first orbit, so it is having an energy of minus 13.6 electron volt. So if you need to take out this particular electron which is present in the first orbit of hydrogen atom, you have to supply plus 13.6 electron volt of energy, then that particular electron will be completely coming out of the atom, or you can take the electron which is present in the first orbit to infinity. Now let us look into the process of excitation. So excitation is nothing but the process of taking an electron from one orbit to another orbit, that is from one orbit to any higher orbit. So the energy required is what we call as excitation energy, right? Excitement means going from lower energy level to higher energy level. So that is what we call as excitation, right? The process is called as excitation and the required energy is called as excitation energy. Here I have shown one simple example. So for hydrogen atom in the first orbit, okay, n is equal to 1. We have the energy as minus 13.6 electron volt, and in the second orbit the electron is having an energy of minus 3.4 electron volt. So excitation means you have to take the electron from lower energy level to higher energy level. Since second orbit is having higher energy, so therefore E2 minus E1. So in order to that is, if you substitute and subtract, we get minus 3.4 minus of minus 13.6. so therefore it can be written as minus 3.4 plus 13.6. so it will give out you a result as 10.2 electron volt. So therefore in order to take out the electron from first orbit to second orbit, or in order to excite the electron which is present in the first orbit to second orbit, you have to give an energy of 10.2 electron volt for the electron which is present in the hydrogen atom. That is the meaning of this excitation, right? Got it? So hope you have understood all these concepts. So just go through it. If you have any doubts, so please mention in my comment box. So thank you very much for watching this video. Meet you in the next video session. Until then, thank you.